Hi. Hello. Welcome to my talk. It's called Writing an Interpreter for Math Equations. Goodbye, LaTeX. It's sort of a show and tell from a project I did as a hobby a year ago when I just had finished my studies in computer science. At the time, it seemed very important to me that it was easy to write math equations on my computer. Now, not so much, but anyway. Let's get on with it. So this is me. My name is Herluf. I work with my friend Mads. We have a company. It's called CodeBoom. We do websites. We like React and Gatsby, which also means that we like GraphQL as well. So if you like any of those things, come talk to us at the networking or whatever else. We love to talk. So on with the talk. This is the question that got me started with the project. It's how do I write a formula on my computer? A math formula, that is. And so I need to specify that a bit more. So the goal is to write like this sort of thing, this sort of complexity on my computer without having a mental breakdown, right? So I like to write this in a lecture setting, right? So somebody is speaking to me and I need to keep focus on what they're telling me, but also I want to write the thing down so I can remember it for my assignment later. So I need a fast way to do that. And so whenever I have a problem like this, I usually go to the only hammer I know, which is JavaScript and web development tools. But it's also healthy to ask yourself is, whenever you have an idea, does this need to be digital? Like, does this need to be something that's software driven? And so I tried to do that because somebody told me I had to. And so how about writing my handwritten notes? That wasn't an option for me because my handwriting is so ugly. So I have pages and pages of uglily written notes that some of them I couldn't even read myself, which is unusable. And the faster I had to write them, the more ugly they got. So not an option for me, at least. So I have one person that could actually use this software, which means that there's like it has a reason to exist now. And also it seemed like a funny project. So the next problem, what are the existing digital solutions for this? Like, how can you write math on the computer now? And at least in academic settings, it's LaTeX. But LaTeX is sort of difficult, right? It's verbose, to say the least. This formula right here, it's the same size as the one I showed you earlier. The one I showed you earlier was also made in LaTeX. I can write this quick. Like, I can't write this in a lecture setting. I can spend an hour doing that, but not at a lecture. So I had to find a lighter syntax, right? And I think most of the problems in LaTeX comes from the reason that you also need to be able to typeset all sorts of different text in LaTeX. So there needs to be commands for headings and tables and all sorts of different stuff. This bloats the syntax, and so the math thing needs to be more verbose. You have to write math BF for boldface. That's really verbose. So what I set out to do is make some sort of markdown, lightweight syntax for math equations, right? So now I have a quick aside, just to make sure that you know what I mean when I say what you see is what you get. So there's this concept, at least in when you make editors, for instance, code editors or Word, that it's called what you see is what you get. And this is basically the problem that Word solved, and I think it's the main reason for its popularity. Is having the actual end result be the place where you also edit your document. So as programmers, we're really used to this thing, right? We're used to having the source code on one side and then the product on that side, like HTML, and then you have the actual website. But this is actually not that efficient if you quickly want to get to the result that you want. And it's also really, in a note-taking situation, it's not that important that it's aesthetic all the way. So you can go to a solution like this one, a sort of instant hot module reloading, if you want to think about it in that way. So now I can actually formulate a challenge for myself. I want to write a what you see is what you get math editor, right? So an inline math editor. Sort of ambitious. so I thought I could do this. We'll get into if I actually could do it later, but first we'll discuss how I chose to tackle the problem. So maybe you're thinking, but how do you actually do this? I did as well. So I started like analyzing the problem. So I thought about the different stages the data was like would go through. So the first one is user input, right? Some user writes some input to my application, supposed application, in the syntax that I define. I'll get into like that a bit more later. Then some parsing happens. You understand this. You try to understand what the user meant by the input, and you try to move the user input to some other data structure. In this case, it's an AST or a abstract syntax tree. It's named by computer scientists, as you probably have figured out. So this is a tree structure. For those who aren't that familiar with trees, think of it as a nested JavaScript object. So at the root of this object, just a second, I think I actually have a pointer in this thing. At the root of this object, there's a division. It's equivalent to this division over here, right? And then we have some leaves. There's a 1, a 2, and also a constant, alpha, right? But we haven't just arranged this user input in a random way. We've actually quite given it some meaning. Like the operator plus has a lower precedence than the divider. So that's why it's lower in the tree. You do additions after you've done all your divisions and multiplications, right? So we've also tried and like understood somewhat of the meaning, something like a bit of the meaning that the user had. And so you have this data structure now. You've understood what the user wanted to type. Then, oh, the pointer. How to go. Then you render it. This is probably pretty familiar to you, rendering. That's supposedly what most of front-enders at least do. You have some data and then you show it in a pretty way to the user. But if we're doing what you see is what you get, this is sort of fluid, right? The user enters like a bit, like one character, and then you need to do this whole thing, understand what they meant and what the current meaning of their total input is, and then render it again. So I go, like this is an overview of how you transform the user input to something pretty. So I'll go a bit into like the two processes, the two arrows on my slide. So the first one is parsing. And what do I do there? First, I define a syntax. You're pretty familiar with syntax. It's the things you can say in this language. So in JavaScript, you can say ampersands for and, like a Boolean and. In Python, you do the literal and with letters. In my math language, you can say alpha. That will translate into the symbol alpha, the Greek symbol. So I have to like make a great specification of what's actually possible to say in my language. Think of it as the words in my language. Then I need to do something called tokenization, which is just splitting a sentence that the user said into its words. So splitting this thing up here into its like smallest parts. And then I have a stream of words that I need to pass to a piece of software called a parser. I'll show you later how to do that in JavaScript, which constructs the tree for me, which makes like actually takes these words and makes a data structure that I can use in the rest of my application. So now I've gone through, just to reiterate, the parsing step. And now we'll go on to the rendering step. How to take this tree and actually show it in a pretty way. You have the tree, right? So you need to start somewhere to start showing it. And a sort of obvious place to start is at the root, right? You start there. And then I'm gonna say a complicated sentence now, but it's really, when you get into it, it's not really that much. But you will recursively call a rendering function on the root, which then in turn calls each of the children on that node, and this resolves to an end result. I'll go through it step by step, because like that sentence might have gotten like 10% of you. I can see it in your eyes, like, okay, yeah, cool. But what happens is I start at the top, and then I go to the rightmost child, and then I go to the left and go through the whole tree. So we start here. How to show a division line visually? It's a line. How to show a 1? I just showed the one. I need to choose some font, but that's it. Then we have the parentheses. You show those. However you want to do that, you can do it with SVG. Tried that, didn't work that well. Maybe don't go that way. But then you have a plus. You have more of the leaves. There's a 2, and then alpha. It's the keyword. So you show the alpha symbol. Just a side note, actually all the Greek symbols are in the UTF-8 standard definition, so you can show all the math symbols in the browser, but it's hard to make them the right size and color and that stuff. Also, you need to choose a font that actually implements them. So if you have this funny font, then it's not going to have the Greek symbols in it. But that's actually it. That's how it works. Yeah. I'd really prefer if the questions were at the end. Sorry.
How do you know where to put this schema? Because you don't know how I'm actually going to go into the tree.
Yeah. Hopefully, I'll show you how it's working, and then it will make sense. Yeah. Otherwise, please come and ask me. I can also send you the code. This is how this is pseudocode, but sort of JavaScript, right? And it's also sort of React. This is how I chose, thought I could tackle the problem. Spoilers, couldn't. But supposedly you were supposed to be able to make a render function, I hope you can see this, which takes a tree, then it has a switch, checks the type of the root node of the tree, and then if the root node's type is a leaf, meaning it's a 1 or an alpha symbol maybe, you return a React component that's able to show that leaf, right? If it's a 1, it shows the 1. And otherwise, for other operators, like a fraction, you have another React component that's able to show the fraction. But for the operands, you have to call the render function first to see which React component they resolve to. So you actually call for the rightmost child first here, get a result for that, and then you pass that to the fraction so it knows what to show on the top, right? Hopefully that makes sense. Sort of not exactly the same order of execution as the circle I showed you earlier, but yeah, sorry. Anyway, enough theory. Did it actually work? I'll let you decide. So it's demo time. So the second half of my talk is about the actual application I ended up making. So it is here, over here. So I named it Blaze because every cool application needs a cool name, right? So it's really inspired by Python's Jupyter Notebook, if any of you tried that. But it has like a block structure, and you can write text, and you can also write, in Python is Python, but here you can write math. So I have a text block, which can go hello host.js, right? And then there's a math block. And now for the big reveal, did it work? So I'll do the equation that I showed in my example as well. And so the observant ones of you already know that no, it didn't work. At least not the way I wanted it to work. This is not a what you see is what you get application, right? Because I have some number input here, and I actually have some visual output up here. So I spent almost a month of my free time trying to make this thing, which was a great learning experience, but not that production didn't have that much to show afterwards. The problems I ran into was I had a great deal of problems with actually trying to place the cursor in the equation in the right place. For instance, here in this fraction, say you want to navigate with your arrow keys and your cursor is on this side of the parentheses. If you go left, go this way, are you supposed to end up here or over here? I'm not really sure. I have to make a choice. I could end up here. Most math applications, existing math applications like Maple and TI Inspire, end up here. And so there's a bunch of choices you have to make with math equation navigation. And that ended up being a really big problem for me. Also, I had some great performance issues. If my equations were I don't know, triple the size of this, my parsing algorithm started being so slow that the whole application started lagging, which is not good. I only have a single math block. This will not be sufficient for my studies. So yeah, so what I ended up actually doing is I joined the dark side. I used a project which is really nice called LaTeX, which recreates LaTeX rendering logic only in the browser. It's really fast and it's also really nice, so it solved my performance problems. But it actually means that what I do is I translate the user input to an abstract syntax tree, and then I translate that tree into LaTeX. So I sort of made a wrapper around LaTeX. Yeah. So if you can't beat them, join them. Yeah. So yeah. So I don't know how I'm doing on time, but I want to go slightly into how I actually implemented it, so that hopefully I can inspire someone to write a parser in JavaScript. Also, I haven't shown you any JavaScript, and it's supposed to be about that. So first I need to define the syntax, right? So here is my language definition. It's called language, promptly named, right? So here is the object that defines whatever can be said in my implementation of math. It states everything you can say in math. So you can say a lot in math, but it's short compared to English. But for instance, I have this negator operator here. And what's pretty cool is I can actually negate relations. So say I have an alpha, which is less than some beta, right? Say I've done some research and I discovered that's not true. Then I can write not before my relation, and then it actually crosses out the relation. Neat, okay. So say I'm more sassy than most mathematicians, and I want to be my negator to be na instead. So my application is just running on like a basic create React app. So it reloads whenever I save this file. So now I can just write alpha na less than beta. And now my language contains na instead. This I thought was pretty cool, because then you could have users define their own like keywords for different tokens and make the language that they wanted to make sort of their way of writing down math. Also, most mathematicians are pretty picky, so they want to do it the way they want to do it. So by doing this, you'd have to make this into a variable, right? But it's totally possible. So this is how I define the language. So how do I actually parse it? I parse using a library that's really cool called Nearly. If you have one takeaway from this, it's that Nearly is cool. It says so itself. Nearly is a fast, feature-rich, and modern parser toolkit for JavaScript. It helps you create a big matching machine that can take tokens and produce abstract syntax trees. And it has a special format. So I have a file called blaze to tree. I called my syntax blaze as well. So both the application and the syntax is called blaze. Confusing. But the format is called any. And this takes blaze and converts it to a tree. This is why I named the file like this. And so it uses a library called moo to actually tokenize the thing. I don't know why it's called moo. It also has the logo, like a cow for a logo, but it's just a lexer. I'm not sure why. But Nearly provides this special syntax for actually creating a lexer. This is pretty involved. I won't bore you with the details, but basically you can see here that I have a level for each level of precedence in math. So this one is addition and subtraction. This one is multiplication and division. And then there's also what I call large stuff, which is sums. So don't know if, like, whenever somebody needs to show you math, like hardcore math, they go, look at this sum. It's so difficult to understand. And I can do sums as well now. So you'd go like 1 divided by I. And also to show you that I actually solved the performance issues, here's this sum divided by itself a bunch of times. So it's okay now. Mostly due to LaTeX, not of my doing. But this specification here, together with Nearly, actually just produces a big matching machine, which creates the trees for me. And if you want to know more about it, then you're pretty weird, but also ask me about it later. And so the last thing I want to show you, I'll mess up the sound, right? Sorry. The last thing I want to show you is my function that brings the tree into the LaTeX or LaTeX syntax. It's just, it takes a tree, produces a string, I pass the string to LaTeX, it renders the equation, right? And so it takes the tree. This is really similar to the pseudocode I showed you earlier. This is called Parse. It should be called Translate, but didn't name it properly. It takes a tree, then instead of a switch, it has a bunch of if sentences, but really it just matches on the type. It says if it's a level 1 operator, meaning it's a plus or a minus, it will recurse on each of the operands, like left and right hand side. And then it will call the toLaTeX function I defined in my language specification. It's in here. So for instance, if I wrote gamma, the large gamma, the toLaTeX function would actually produce just gamma. But for instance, a sum, you can see the toLaTeX function is a bit more involved. It has an up and down, that's the ranges on it, and it also has a body, which is the actual content of the sum. And then it produces, depending on if there is some ranges or not, it produces a different string, right? But so hopefully you can get an overview of how this whole thing actually operates. It just basically solves the problem of trying to understand what the user actually input. So the key takeaways for me is in this project that you might set out to do something and then realize it's not possible, at least for you. And that's okay. I still learned a lot, and I had a bunch of fun making this. Also, math equations aren't as relevant now when you do front-end code. Don't need so many sums anymore. But yeah, does anybody have any questions? No? Yeah, it's pretty weird as well. So, thank you for listening, though.